Okay, I'm going to try and make this video a little bit shorter than the last time. I know we had a lot to talk about on 3.5, but here comes 3.5a, day number 2. And again, we'll hit these review questions relatively quickly to make sure that you've got some concepts that are going on. Ultimately, key word on every single one of these first three is the word solve. And if you end up coming across any kind of solvings that are exponential or logarithm, then they all dictate that you need to exchange them. Exchange them into their alternate form so that you can get the x to be in the right place and actually solve for it. For instance, if I'm dealing with 10e to the 2x equals 5, I'm going to isolate the exponential. First thing I would do would be make it e to the 2x is equal to 1/2 by dividing the 10 on the other side, and then straight up into the exchange concept. And an e would definitely lead you to an ln. ln of 1/2 is equal to 2x, and then from there it would just be taking the ln of 1/2 and dividing it by 2. Second question, same kind of idea. Looking at a logarithm, still isolate the logarithm. Make sure there's nothing else around it. In this case, that one's alone. So that would be 10 to the second power, because that's a log base of 10, to the second power would equal 2x minus 3. 10 to the second power, 100, add your 3, divide by 2, you're ready to rock and roll. Last but not least, the 7 to the x is equal to 21. That would end up becoming log 7 of 21 is equal to x, and then they want you to use change the base formula, which would be, and I always use ln's, ln of 7, or ln of 21 over ln of 7 is equal to x, and that would just generate a number, okay? Be aware, and I don't know if your teachers have talked to you about this, but it might be worth you asking the question of whether or not you know how to plug in a log with a different base into your calculator too as well. Ask about it, and that would be a nice question to bring up in class. What is the general exponential model or equation for growth or decay? That is the part we're going to be really talking about today. A, which is the final amount, which is a sub o, and then we've got e to the kt. And keeping in mind that a k value is your rate, either positive making it growth or negative making it decay. All right, so that's the one we're going to be working on primarily today. So let's find out what's going on here. Now, steps to solving any one of these word problems. Again, I cannot emphasize enough how many times you're going to actually be given questions where, number one, you're going to want to actually find k first. And once you find that value of k, you're going to want to store that value of k in your calculator so that you can, two, solve for either one of the two possible ideas that comes next, which is either you're solving for time, and you plug in the rate and a sub o and a, and you solve for time, or you're solving for a, where you plug in the rate and a sub o and time, and you solve that one using your calculator. Be aware, one uses ln quite often, the other one does not. Mostly this is a plug and chug kind. If you're solving for time, you're trying to get that variable to come down from upstairs, and in doing so, you're going to end up having to use the ln. Make sure your time always matches your units of time when it comes to your rate. So if your rate is in hours, make sure that you're talking about your time in hours, okay? It's a very important thing that the rate time and the time you're actually outputting do specifically match. Now, I'll give you an example of such a thing. Here's this first example. It says a specific type of bacteria triples every 20 minutes. Okay, now this is going to be a concept that we're going to have to look at here. The tripling amount takes place over a minute time cycle. And if the amount of bacteria that originally started, this is your a sub o, is present initially. Now, if I want to know how many are present after 2 hours, the first thing I'm going to have to do is I'm going to have to figure out what k is. So there's like a separate problem over here on the side where we're going to need to talk about what is the k value. And that comes from this tripling amount. So if I said I had 1 bacteria, how long would it take for it to become 3 bacteria? E to the kt. Okay, now in case we're really thinking about here, we're really trying to figure out what kind of time value that we should put inside here. Now, I don't want to put, if I put the number 20, then everything is going to be in minutes. If I choose the same exact question, but I do it a separate way and say 3 is equal to 1, e to the k, but instead of putting 20 minutes, I ended up putting something in terms of hours in there, I would want to make sure I understood that 20 minutes is a third of an hour, and I'd put in 1/3 right here. Now, I'm going to probably stick with the value of minutes just to keep it straightforward and explain how that would take place. So if we do a minute concept on this, I would end up with the ln of 3 would equal 20k. And in the end, let's see what our calculator says about that particular value. So ln of 3 divided by 20 would end up giving me a k value of 0.0549. Okay, now I'm going to store that as alpha k, and that can be used for a little bit later. Now, when I use this answer right here, in my next following question, I've got to make sure that the number of time units matches the k value time units. Remember, this one we did in minutes. So if I set up the next question, which is A equals 230,000 e to the kt, I can't put the number 2 in here. I have to put it in terms of minutes. So I would put in 120 here. So do you get the idea that the number of k unit time units has to match the actual time units in your question? Now, if I plug this guy in, the calculator, this is a plug and chug looking for a final value, 230,000. I think that's enough zeros. Second, e to the alpha k, again, this takes away the idea that you have to plug it in every time, times 120 would tell me that there happens to be a whole lot of bacteria in this case. 1676 7 1 2 3 4. What are we talking about here? We're talking about 176 million in just 2 hours. Now, this is one of those reasons why your body has to react so quickly to a bacterial infection, is because they can grow relatively fast. 3 is not an unheard of concept. So your body, what it does to react to these kind of things is it, of course, raises your temperature. And a temperature is a natural reaction that affects the K value. In warmer environments, the bacteria cannot reproduce nearly as fast, so it's your body's way of reversing that kind of effect or slowing down the K value. What is the doubling time for the bacteria? Doubling time in this case is just to figure out how long it takes one bacteria to become 2. It's regardless if it's 230,000 to 460,000. It'll still be exactly the same. E to the kt. Now you've already calculated the K value in this particular case. The time value that you're going to end up out of this is going to be, in essence, it's going to be in units of minutes. So ln of 2 is equal to kt, and we'll end up dividing by k, and we'll get an answer for ln of 2. Hold on just a second. Oop, not that one. ln of 2 divided by alpha k, and we're looking at the time minute for it to double is 12 minutes and 12.61 minutes is how long it would take. All right, so keep in mind of what's going on there in terms of matching units of time. All right, that's super important. Here's one. Sophia wants to triple her savings after 15 years. So what is her fixed annual interest rate if it's compounded continuously? All right, so we've got a compounding continuous concept. That's definitely going to make us think about APERT. Okay. She wants to triple her savings, regardless of how much money she has in there. She's going to triple her savings of $1 to $3, or she's going to triple $1,000 to $3,000. It'll take the same amount of rate, in this case, for 15 years. So let's say we're going to take $1, turn it into $3. Boy, she's not saving a whole bunch. E to the R, and in this case, she wants to know what it's going to take for 15 years. Now, this is a really good question because you should be looking at trying to put away some money this time around in your life, or a little bit here soon, about what kind of interest rate should I be searching for to actually pull that kind of concept off. Well, the ln of 3 would be equal to 15R in this case, and let's find out what kind of interest rate that Sophia needs to find to be able to pull off a tripling of her amount in 15 years. So ln of 3 divided by 15, she needs to be searching for a 0.073 interest rate, or a 7.3% interest. Not unheard of if you're kind of like looking in terms of the stock market nowadays and are a little bit risky about it, but totally doable if you wanted to triple your money in 15 years. So if you're really smart, little Sophia right here would not be asking for her college money. She'd be asking for grandma to put in money into an IRA or an investment account so that 15, or even better yet, 30 years from now, whatever amount grandma gives me is going to end up being not only tripled, but 6 times as much money in 30 years. So maybe, try and be nice to those people that you find old and unappealing. Abby deposited a certain amount of money in her savings account 10 years later. Okay, so there's some important information. She has $3,450. Her account had been earning a certain amount of interest, which is reasonable, 2.34% interest, because it's not much, compounded quarterly. How much did she actually deposit originally? Because she's apparently got Alzheimer's disease and can't remember. $3,450 is the last deal. The principal that she's got in there, is what she's trying to find. 1 plus the rate, which is 0.0234, divided by 4, because it's quarterly, raised to the 4 times the time, in this case was 10 years. Now, the part I want to point out in a lot of these kind of questions that are like this, especially solving for this particular principle, is that principle is basically attached to this entire thing by multiplication. And if you could find out what this number is, it would ultimately just divide into 3,400. A relatively easy kind of question, but you just got to be careful with how you plug it in your calculator. 1 plus, I'm going to nest the actual parentheses here, 0.0234 divided by 4. And ultimately, I would almost say it might be better just to get just the answer to the base, which is this piece, and then raise that answer to the 40th power, and then take your 3,450 and divide by second answer, that answer that you previously got. And the amount of money that she put in there was $2,732. And we'll put down the 6 cents too, just because it does matter. Pennies matter. All right. So ultimately, really look at your solving premise. Many times when you're solving for stuff that's in the lower part, it's pretty much just a division concept. But as soon as you start solving for things that are in the exponential, you're definitely dealing with a logarithm to get it to come down. The tripling time for Abby's money here, how much time is it going to take for her to actually triple it? Tripling her money would still be based on the fact of her, not even her original deposit. Her original deposit's $1. Her stuff is $3 in the end. She still is using a quarterly compounding concept. So we've still got 1 plus 0.0234 divided by 4 raised to the 4 times. And now we're talking about time. Now, this particular question is definitely going to be solved with a logarithm, because ultimately, to get this 4t to come downstairs, we got to use a logarithm to do it. Now, in essence, we're really kind of dealing with 3 is equal to, because the 1 divides over on the other side. I'm going to grab my calculator to kind of look at that base value. The base value when we did it was this 1.00585. And That's going to be this 1.00585 number that's right here, raised to the 4t. Now, the only way to really solve this is to use a logarithm to solve it. So we're going to do the base is equal to this piece and is equal to 4t. So we've got log base, hold on, I got to move this down just a little bit so you can see it. Log base 1.008585 of 3 is equal to 4t. And like I said, most of the time when you're trying to evaluate these logarithms, they're much easier to evaluate with an ln. So the ln of 3 divided by the ln of 1.00585 is equal to 4t. I'm going to move that over. 4t. And then ultimately, whatever this logarithm is, it seems to just be needed divided by 4. I don't know why my calculator's thinking here. Hold on. Got to go back down to the bottom. So the ln of 3 divided by the ln, and it's just me. I happen to be one of these kind of people that really thinks the ln is more appropriate to most of these questions than just doing common logs. And poor little Abby's got to wait 47 years before she can actually get her money to triple. Now keep that in mind. Tripling that money took Abby how much work of her own to get through it, and that's exactly right, none. She didn't work a single bit to make her money triple. This is why smart people with smart money don't work. They end up putting their money away and making their money work for them. So be smart about it. Suppose a colony of bacteria is growing exponentially. That's nice to know. 14 hours is required for the bacteria to grow from 3,000 to 4,000. So initially 3 becomes 4. It's going to be ultimately, and then it says find the doubling time. Well, you're going to need to use this initial value to figure out what the k value is first. This is one of those I have no k concept, so I better find k first. And I don't know why I just drew an equal sign on this side. That makes no sense. Let's see what we got here. E to the k, and in this case the time is 14 hours. Now let's keep in mind that the hourly rate here is 14 and it's in terms of hours. Might write myself a little note. That's an hours concept. And I divide and take the ln. So it's really the ln of 4/3 is going to equal 14k. And k in this case is going to end up coming out to be, let's see what good old Donna has to say. The ln of 4/3, and then take that answer and divide by 14. Now I've got a nice alpha, oops, no, I'm going to store alpha k so I can use it later, and that is 0.0205. Now what you get here is you kind of like your calculator becomes the storage device, your paper becomes where you keep your ideas down. What's the doubling time? The doubling time in this case would be to take it from 1 bacteria to 2 bacteria again, and that's e to the kt, and we're talking about the ln of 2 being divided by ultimately alpha k, and we'd end up with that the time for it to double is about 33.7 hours. Now, here's the thing. If you're in a patient in a hospital, would you hope that maybe your doctor knows how to calculate what the infection is doing over time, or at least maybe the technician that is taking a look at your samples knows how these exponential growths and decays work? If not, hey, you're at the mercy of what they call a doctor's practice. Yes, you're being practiced on. Think of it that way next time, because you never know. How old is the actual fossil if only 13% of it is still around? Well, before you can even do this, you need to store your rate before you can even get there. Use the rate you stored under C in your calculator. We may have stored it earlier, but I'm just going to go back to the original concept that the carbon-14, I'm just going to go up here to find its number of years. I think it's 5,715 years. There it is right there. I'm going to calculate a half-life. So that's what you're doing here is your carbon-14 dating. So I'd say 100 grams becomes 50 grams and e to the kt, and the time is 5,715 years for carbon-14. Well, let's find out what that is. That's the ln of 1/2 is divided by 5715 is going to equal your k value. Let's find that. The ln of 0.5 divided by 5715 would give you this guy, store alpha k. And we've got that k value in there. That's that negative 1.21 times 10 to the negative 4. Now, that takes care of part 1. Now we only know that there are 13% of the original 100% situation, and that's how we use those percentages. I like it this way because it seems to make sense to me. If it was 100 grams, there's only 13 grams left. Keep it in terms of 100, and the percentages won't elude you. E to the kt, and we'll find out how old the sample is. Maybe it's the Dead Sea Scrolls. We'll say here the divide, and we'll get the ln of 0.13 divided by k is going to end up giving me time, and the ln of 0.13 is divided by alpha k ends up turning out that this sample is 16,821.6 years old. Okay. Now, ultimately, what you do in dating that kind of stuff, if you're an archaeologist, you would really take a very close look at what the percent is left in the sample, and in doing so, you would get a very accurate, very accurate answer of how old that particular sample is. We use carbon-14 radioactive decay. To do dating like this, we have the atomic clock that's in New York City that all of our cell phones run off of, is done by a carbon-14 dating as well too. So in terms of accuracy, it's pretty friggin' accurate. All right, I hope this one was a little bit shorter than the last one and you get some stuff out of it. Give that worksheet a try, and good luck.